All right, we're going to start with an example similar to the one we did yesterday. Okay. One thing I do want to kind of talk about it is essentially if we drop something, is it going to take longer to hit the ground, or is it going to be the same amount of time? Okay. So what are we moving at a horizontal constant velocity today?
Spark.
A spark?
Spark.
Spark the lizard? Okay. All right. So let's say Spark is on his like cat tower thing that Miss Schaefer has for him. He likes to sit on the like round part.
He's wearing cool sunglasses too.
Okay. I mean, he is Spark.
Yeah.
So his legs are not looking great at the moment, but hey, trying to draw this fast. We do have a short schedule. All right. All right, so we've got Spark on the thing, okay? Let's say that he jumps off of the cat tower thing with a forward velocity of what?
100 meters a second.
100 meters per second. Okay. Okay. How tall do you think that cat thing is?
10 meters.
I don't think it's that tall, but we can go with 10 meters if you really want. I think it's probably closer to 1. So we're not going with realistic values then? Okay. Just making sure. All right. I mean, the 100 meters per second is not particularly realistic anyways. So he jumps off with a forward velocity, so perfectly horizontal velocity of 100 meters per second, and is 10 meters above the ground. So let's say we want to know the distance here. But before we do that, let's say that when Spark jumps off of this, he knocks, say, like a grape or something that Miss Schaefer was trying to feed him off of the tower. Okay? Good? Which one's going to hit the ground first, Spark or the grape?
Same time.
Okay, they should hit at the same time if we are ignoring air resistance, which we are in this class because air resistance is hard to calculate. Cool? So, just to make sure that you guys are aware of that, we want to know how far he's going to go. So what should we look for first? We did one just like this yesterday. Time. Okay? What's going to give us our time? How can we find it? If you look back at the example from yesterday, it's probably a really good hint.
Square root of 2x over 8.
Yep. So yesterday we got this equation from our x equation, and we said we can use this as long as our vertical initial velocity is 0. You guys remember that? Yeah? So in this case, Spark's velocity is all horizontal, so our vertical initial velocity is 0. We can use this. Okay, it's a nice shortcut equation. So we can just put in 2 times 10 divided by our acceleration of negative 9.81. Okay? What am I missing again? Just like last time? Okay, so because we're calling the starting position 0 and down negative, we do need to make this negative as well. Okay? All right, what do we get? Should be really close to 1.
.4243.
1.43? And you did square root it?
Yes.
Yeah.
Oh, yeah.
And just to show that it does work unit-wise, oops, this is meters, not meters per second, sorry. We have meters here, we have meters per second squared. Our meters would cancel out, and the square root's gonna get rid of our squared on our seconds, so we would in fact get units of seconds. Good? Okay. All right. Now, we just need to find our horizontal distance. And since we want a distance, we want to use the distance equation. Do we have to use the whole thing though?
No.
What's 0? Horizontally, do we have any acceleration?
Yes.
No.
No. Okay. So we're going to assume that there is no air resistance. So once Spark jumps off of this, he's going to go at a constant horizontal velocity. Okay. Because it's horizontal, acceleration from gravity, up or down, is not going to affect it. Okay? So our acceleration is 0 in the horizontal direction, so that goes away. We can call our initial position 0, so that's going to go away. All we're left with is VT, or the classic equation you learned in grade school, where your distance is your velocity times your time. Okay? So we get 100 meters per second times our time that we found there, which is 1.43 seconds. So what do we get?
.143.
143. We do get the correct distance. Any questions? No? So this is a slightly less formal way of doing this than the one we did yesterday, where we actually wrote out, like, this is our horizontal, this is our vertical. So once you get used to them, you can do them like this. If this confuses you, stick with the whole, this is my horizontal stuff, this is my vertical stuff, and kind of keep them separated. It is easier to remember what numbers go where that way. Good? Any questions? No? All right. So now that we've kind of reviewed this, I do want to talk about the next thing with accelerated motion. All right, we're going to pretend that currently there is no friction, okay? So we have a nice ramp here, like so. Let's say our ramp, what incline do you want on our ramp? So what angle do you want there?
30 degrees.
30 degrees? Nice and easy. Okay? And let's say we have a box sitting on our frictionless ramp. First question, if this ramp is frictionless, is the box going to be moving or standing still? It's going to be moving, okay, because there's nothing to stop it from moving. We don't normally have frictionless ramps in real life, and so if we set a box on some sort of ramp, it generally doesn't move, okay? If we take away the friction, it is going to slide. Okay, so this box is going to be moving down the slope. Okay? All right. Now, let's say that this box has, yeah, let's go with that. A mass, what mass do you want it to have? I'll let you make it up.
2 grams.
2 grams, okay. So 2 grams would be, there we go. That's 2 grams in kilograms, right? I think. Just doing it in my head. No, there would be another 0, wouldn't there? Okay. All right, so we have a 2 gram box, okay? And I want to look at what is the acceleration of this box, okay? Where would our acceleration be coming from? Any ideas?
Gravity.
Gravity, okay? The only force that's probably acting on this box, because we said friction is not a thing, is gravity, right? Yeah? So, we know that gravity points directly downward, right? Yeah? So this is our force of gravity. Do we know some sort of possible equation that might relate force to acceleration?
I think it was in
F equals ma. Okay, so we've got F equals ma. That's going to be very useful for this equation. Now, this is getting into a little bit of some weird vector stuff going on here. Okay? Our direction of motion is this way, right? It's down the ramp. But our force is into the ramp. Okay? So we actually need to figure out how much of this force is just pushing the box against the surface and how much of the force is pushing it down the slope. Right? Yeah? Okay? We are going to do this one in variables because we'll find out something very useful at the end. Okay? Good? All right. So I want to draw this sort of force triangle out to the side. We know that the force of gravity, or its weight, okay, is going to push directly straight down. Okay? We know our acceleration is going to go along the surface of the ramp. Okay? Actually, that's not really parallel to the surface of the ramp. We'll make it a little bit better. We know that the force pushing it down the ramp is going to go parallel to the surface of the ramp, right? Yeah? We also can kind of draw on this horizontal line, like so. And we know this is perfectly vertical. We know this is perfectly horizontal because we drew it in, right? Yeah? So we can put a nice right angle sign right there. Okay? So we've essentially said, hey, this is pretty much the same triangle as here, right? Yeah? Okay? Sadly, this is probably not going to be the most useful triangle to use once we actually start looking into this, right? The more useful one is probably going to be using our force vectors, okay? So if we draw this in, we know that this side is going to be part of this equation here, right? Or part of that force, not equation. Because our force down is the full force of gravity, our full weight, and the part that's going to push it down the ramp has to be small. Okay? So even though it's going to be in this direction, it's not going to be that big. Okay? Now, we want an orthogonal basis because that always makes our life easier. So we want something that's going to be perpendicular to the surface and is still going to have meaning. Does that kind of make sense? Is this bringing back vague memories from freshman year? Some people, yeah. Some people, definitely not. The other force that is actually going to be useful here, that is going to be at a 90-degree angle to everything, is going to be our normal force. Do you guys vaguely remember that? Okay. Normal force, by definition, means that it is perpendicular to the surface. And in this case, the one we want is the one that goes here. Okay, so this is our normal force. This is the force down the slope. Good? Yeah? Now, part of the reason why I left this triangle here is because we know that angle is 30 degrees. And this triangle share that angle right there. And we also happen to know that by the way we've drawn this and by its definition, the normal force is perpendicular to the surface of the ramp. Okay? So we still do have a right triangle, which is always nice. All right, so this big triangle is a right triangle. We know this is 30 degrees. What's this angle? 60. Oh, man. Hello. Yes. Certainly. We know you are in the office. All right. We also happen to know that because this is now a right triangle, this is 60 degrees. What's this one? 30. Okay. So on problems like this, it is nice and easy to remember that this one and this one are always going to be the same. This one's always going to be that minus 90 degrees. Good? Or 90 minus that then. Good? Okay. We will do quite a few of these problems later on once we get more into force. But what we want to really look at today is our acceleration. Okay? Yeah? Everybody good? Okay. All right. So what we want to do is find an expression for our force down the slope and our normal force in terms of what we would know, which is our weight, right? Our force of gravity using MA is going to be our mass times the acceleration of gravity. Cool? Make sense? Okay. All right. So we need some sort of expression to say what force down the slope is and normal force. What can we use? Hint, we have triangles.
Pythagorean theorem.
We could, but that is not going to be the most useful in this situation because that will have both of our variables in it. So it would work, but it's not going to be the most useful.
Wait, what are we trying to find?
We're trying to find an expression that says something along the lines of force down the slope equals something with force of gravity in it, or normal force, either one.
Sine.
Okay? We can use sine. Here, it might be easier if we write it like this. Sine of what? Sine of 30 equals
Force down. Force of V over force of V.
so our force down over the force of gravity. So we really want this. So force down equals force of gravity sine of 30, right? Yeah? Okay. Then we can pretty much do the same thing for our normal force just using cosine, right? Yeah, I'm not going to write it out like this. We're just going to multiply both sides by our hypotenuse. So we get normal force equals force of gravity sine of cosine of 30. Good? Any questions? No? Okay. Now, what we're really looking for is the acceleration of our box, right? Yeah? And the acceleration of our box is coming from the force down the slope. Right? Yeah? So we want to find Our acceleration, like I said, so we'll solve this for acceleration real fast. Good. All right. And we already have an expression for force down the slope. Yeah? So we're going to sub this in for F here. Oh, man. We're almost done, too. I guess we'll have to finish this tomorrow. Have a good day, guys.